Bayesian optimization with automatic prior selection for data-efficient direct policy search. Among the data-efficient approaches for reinforcement learning, Bayesian optimization can successfully learn parameterized policies in only a few iterations. One of its key features is that it can leverage priors to speed up the learning and to better adapt to unknown situations. In this work, we assume that a set of predefined priors is available, but we do not know which one matches best the current situation. To exploit these priors, we introduce a novel acquisition function for Bayesian optimization that balances between how likely the prior is given the data and how helpful this prior can be for the optimization. We call this acquisition function most likely expected improvement, or MLEI. We demonstrate our method on a six-legged robot with an unknown damage that has to learn to walk again. The priors are generated beforehand in simulation and are encoded as the mean function of traditional Gaussian processes. We used here 15 priors for each of 6 different conditions plus the intact robot. That is, we can use any of the 105 priors if they are helpful. Let's suppose that the robot is damaged with a damage condition that was among the priors. At the first iteration, the robot tries the best behavior among all its priors. The result differs from its expected performance, so the robot updates its performance predictions for both this gate and similar ones. At the next iteration, optimizing the MLEI acquisition function means that we jointly search for a prior that has the best likelihood and for a gate that has the best predicted performance. After few iterations, the MLEI finds a high-performing gate in spite of the damage and the many differences between the priors and the real robot. Here are the final results for 5 replicates of this experiment after 10 iterations. Here is another experiment on a damaged 6-legged robot learning to climb stairs, in simulation this time. The priors are now gates of a robot climbing stairs with various kinds of stairs but with no damage. There are 20 priors to choose from. Suppose that the robot has to climb a new kind of stairs. At the first iteration of Bayesian optimization, the robot tries its best gate among the priors, but he fails because of the novelty of the situation. Now, at the following iteration, the MLEI selects jointly the most likely prior and the most promising gate, and the robot performs better. After only 5 iterations, the robot has learned to climb the stairs.